Now let's understand the concept of work. Okay, let us suppose I have a force which is acting like this on a particle, which is this one. Okay, now under this force, if my particle moves from say point A to point B, then the work done by this force in moving the particle from point A to point B along AB is given by work done by F. Okay, so let's call this guy as F. This is my force, and under this force my particle moves from A to B along AB. So my work done from A to B is given by F vector dot RB with respect to A vector. Okay, what is this? This is the displacement of B with respect to A. Okay, so what is this? If I suppose this is my reference point, then this is going to be what? Let's use a different color. This is going to be what? This is going to be RA, right? This vector. And this is going to be what? Oops. This is going to be RB. Okay. This is the displacement of this point. This is the displacement of this point. Therefore, displacement of B with respect to A is going to be RB minus RA. Okay. Which is this vector. Okay, RAB. Okay, this is your RAB or RB with respect to A. So your work done by force F in moving the particle from A to B along AB is equal to the F vector, which is the force vector, into this relative displacement vector, which is RB by A. Okay, it is basically your dot product. Okay, this is a dot product. So I'll just make sure that you understand this is a dot product. So we know that A dot B is equal to what? It is equal to AB cos theta, right? So if this angle is theta, then your work done is going to be equal to your modulus of F into your modulus of RB by A into your cos theta. Okay, so this is in terms of vectors, this is a dot product. This is in terms of scalars, where you have the magnitude of F and the magnitude of relative displacement vector. Okay, and the angle between them, right? Also, what you can do is you can have your F in terms of its rectangular components, right? My F can be written as Fxi plus Fyj, right? Similarly, my relative displacement vector can also be written in X and Y components. So I would have what? I would have RB by A is equal to, let us call this as RB by A X I plus RB by A Y J, right? So now my work done from A to B is what? It is going to be F dot RB by A vector, which is going to be Fxi plus Fyj dot RB by AXi plus RB by AYJ. Okay, we know that I dot I is 1, I dot j is 0, and j dot j is also 1. Okay, and j dot I is 0. So what we get is, let me just get rid of all these things, this and this. Okay, Then if I multiply this with this is I dot j thing. So this product becomes 0. Then this and this is 1, and this product becomes 0. So what I am left with is fx into rb by ax plus fy into rb by ay. Okay, so your work done is component in x direction into displacement in x direction plus component of force in y direction into displacement in y direction. Okay, let's look at this expression again. Okay, what is my work done? My work done is the modulus of force into the modulus of relative displacement vector into the cos of angle between these vectors. Okay, this is a scalar, this is a scalar, this is a scalar. What we are getting finally is a scalar. Okay, so my work done is a scalar, it is not a vector. So my work done is going to have a sign either plus or minus depending upon this angle, but it does not have a direction. Okay, let's look at this concept in this way. Let us suppose I have a force which is this way, and due to this force I have a displacement like this. Okay, now in this case, what is your angle between the force and the displacement vector? It is 0. Okay, therefore your work done is going to be f rb by a dot cos 0. Okay, so your work done is now positive. Okay, so this is f rb by a, that's it, this is 1, right? If however, if your force is like this and your displacement vector is like this, then this angle is what? This angle is 180 degrees, right? Therefore, in this case, my work done is going to be f rb by a modulus cos 180. Okay, so essentially my work done now is cos 180 is minus 1. Therefore, my work done now is negative. Okay, it is minus of f rb by a. Okay, so my work done can be positive or it can be negative. Okay, let's look at another case. If my force is like this, okay, and my displacement is like this. Okay, if this is rb by a and if this is f, then what is the work done? My work done now is f, then I have rb by a modulus cos of this angle is 90 degrees. So cos of 90, so what I basically end up with is 0. Cos 90 is 0. Therefore your work done when the displacement is perpendicular to the direction of force is 0. Okay, let's apply this 0 work done concept to a scenario where I have a force like this. Okay, I have a relative displacement vector like this. Now I know this angle is, let's suppose, theta. So obviously I can have two components of this force, one along the direction of rb by a and other at perpendicular to rb by a. Okay, so my components would be like this. I have along this, if this is my f, this component is going to be f cos theta, right? And this component is going to be what? Does it look perpendicular to you? Let's have it like this. This component is going to be what? This component is going to be f sin theta. Okay, now my work done by force is equal to F dot RB by A vector, right? I can also write it like this: F cos theta vector plus F sin theta vector dot RB by A, right? I have resolved my force into two components, F cos theta and F sin theta, and I am replacing my F by these two components. Okay, so what I get is F cos theta plus, or rather let's get a dot product of this, dot RB by A vector plus F sin theta vector dot RB by A vector. Okay, now if you look at this, F sin theta force is perpendicular to the displacement. Okay, therefore this work is going to be 0, right? Or rather this dot product is going to be 0. So what you get is, this is equal to F cos theta vector dot RB by A. So essentially what you get is, your work done is the component of force in the direction of displacement into displacement. Okay, so I'm just going to write in over here, your work done is component of force in the direction of displacement. Okay, or in the direction of RB by A. Okay, so if you know the component of force in the direction of RB by A, you could simply multiply it with the modulus of your relative displacement vector and you will get the work done, because your cos angle over here is 0. Okay, look, over here your component is this way, your relative displacement is this way, therefore your angle is 0, so cos 0 is anyways 1. So if you get the modulus of this, you get the modulus of this, you just multiply them and you will get your work done. So this is an important result wherein we can find out the work done by knowing the component of the force in the direction of displacement. Okay, now let's understand what is the work done by a variable force. Up until now we have been assuming that my force was constant. However, if my force is not constant, then how do I calculate my work? Let us suppose I have to calculate the work done by a variable force from point A to B. Okay, so what I would do is, I would take a small displacement along this path A to B. Okay, and if suppose I have a origin somewhere, then this vector is going to be my relative displacement of this point with respect to this point, right? Therefore let us call this vector as dr vector, and let us suppose at this instant my force is making an angle theta with the relative displacement vector. Okay, so this angle is, let us say, theta. Therefore my work done in this particular interval, small interval, is going to be what? It is going to be F dot dr. Okay, all in terms of vectors. Therefore my work done in terms of magnitude is going to be what? It is going to be F modulus dr modulus cos theta. Okay, I can also write it as F cos theta, right? I can write it as F cos theta into dr. What I would do is like this, and I know F cos theta is the component of my force along dr. Okay, so I can say this is equal to Ft dot dr. Okay, what is ft? Ft is the tangential component. Okay, this is the tangential component which is along dr. Okay, so I'm just going to write in over here, this is the tangential component of force along dr. Okay, along dr. And I am talking about what? I am talking about the modulus of dr. Okay, this and this would give me ft, modulus of ft. I also want the modulus of dr. The modulus of dr is going to be this small length. Okay, this thing. Okay, the length along the curve that I have traveled. So let us call that length as ds. So my modulus of dr is ds. Just going to write in over here that modulus of dr is equal to ds, which is the distance along the curve. Okay, distance along the curve. So work done during this small displacement is ft into ds. Okay, this is into and not the dot product. This is a scalar, this is a scalar. Okay, so this is ft into ds. Therefore your total work done from A to B is going to be what? Your total work done from A to B is going to be integration ft ds, where at point A, what is my displacement? Let us suppose this is my origin. If this is O, then at point A, what is the distance along the curve of A? It is this distance. Okay, so let us say this is S1, and let us say this distance is from origin to B. This distance along the curve is S2. Then my limits of integrations are from S1 to S2. Okay, this is the work done by a variable force. Okay, this is the component along tangential direction, and it is the modulus of that component. Okay, so you have to express your ft in terms of ds, and then you can integrate it like this. The other way to look at it is, you have f dot dr, right, and you are going from A to B. So what I could do is, I have my dr as, let's say, dxi plus dyj. Okay, and I have my f as fxi plus fyj. Okay, therefore your small work done, okay, the work done by this small displacement is going to be what? It is going to be, let's call this as dw. That work done in that particular small displacement is going to be f, which is fxi plus fyj dot product dxi plus dyj. So essentially what you're getting is fx into dx plus fy into dy. Okay, this is your dw. So your total work done is going to be dw, which is work done from point A to B, which is equal to integral fx dx plus fy dy. Your limits are from point A to B along the curve. Okay, along the curve from point A to B, you have to integrate this particular expression so that you could get your work done. Okay, so essentially what you would have to do is maybe express dy in terms of dx, or maybe express dx in terms of dy, and then take coordinates of either x or y, okay, so that you could integrate along this path. Okay, now let's understand when we are going to use which result to get our work done. Okay, my first expression gives me the work done is equal to tangential force into ds integral, or in other words the modulus of f into cos theta ds integral. Okay, so if my theta is constant, or in other words my f is a function of s, okay, then I can definitely use this particular result. Okay, however, if I have a f which is say function of x comma y, okay, so I have a fx which is say a function of x, I have a fy which is say a function of y, then I would have to use this particular expression. Okay, I also need to know what is the path of the curve. Okay, if this is my curve, I know this is my y is equal to f of x, then my dy is equal to f dash x dx, right? Therefore my integral fx dx plus fy dy is going to be what? It is going to be equal to my fx is f of x, okay, dx plus my fy is given as f of y, okay, and I know y is a f of x, therefore I can represent my fy as a function of x. So let us call this as f1x, this would be f2x, and my dy is f dash x dx. Okay, so dot f dash x dx limits would be from x is equal to x1 to x is equal to x2. So this is how you are going to get the work done when you have the forces as function of x and y, and if you have the forces as function of the path along the curve s, then you are going to use this particular equation. Okay, look, the same equations can also be used if your force is constant. Okay, then you would definitely get s, right? This if ft is constant, and what you are going to get is s2 minus s1. Okay, so this is not necessarily a work done by a variable force. The same methods or the same results you can also use when you have work done by a constant force along a curve. Okay.